Hello, my name is Javier Dario Martin, and I'm speaking here as part of a team. The team is composed by Hector Salcedo and myself. We are working on our capstone project for the GCLog program from MIT. Our advisor and project leader is Dr. Chris Kaplis. So the main objective of our capstone project is to improve freight rate forecasting using Quantile Regression and R software. So here we see a simple database. We have a lot of information from different firms. So here we see this column, it's called firm. We have firm AAA, and firm BBB, and firm CCC. Each of these firms is a different firm. It's not a type of firm, it's one particular firm. So here we also have the shipping date, the origin state, the origin zip code, the destination state, the destination zip code, and some other information regarding, for example, latitude and longitude from the origin and the destination. But we also have three important variables here that are the distance, the fuel cost per load, and the line haul cost per mile. So we can define a new variable. It's going to be called a cost per load or all-in cost per load. And this cost per load is going to be calculated as the fuel cost per load plus the line haul cost per mile times the distance. So we can calculate this cost per load for all the data here in this sample, and then we can save all this information in order to work with these values in our software. Before that, I'm going to show you the script we wrote on Notepad++ using R programming language in order to run the script in our software and to analyze the data. So first we see here the data organization. We organize the data here. We analyze the data, checking the linearity, the correlation, and drawing a quantile plot. Then we run the OLS regression, and then we run the quantile regression. At the end of this script, we have this CPL forecasting function that is going to predict the cost per load value given a certain distance and given a certain tau. So if we copy this script and we paste the script on the R script window, we are going to be able to run this script and to see the different outcomes. So this is a capstone project, as mentioned, by Hector Salcedo and Javier Martin. That is myself. Our advisor is Dr. Chris Kaplis. So the first thing we should do is to organize the data. Here we are transforming the data in numbers. Some of this data, for example, the distance, the fuel cost per load, and the line haul cost per mile. We are transforming these values as numbers within R in order to operate with these variables. And we defined two variables, the distance and the cost per load, as I mentioned before. We can then analyze the data. We can check for the linearity of this data. We can plot the distance against the cost per load. Well, we see here that most of the information is in between 200 and 800 miles. So now we can check the correlation between the distance and the cost per load. This correlation is 0.87. And we can also draw a quantile plot. So in this normal QQ plot, we see that our data is not following normally distributed distribution. So here we have this normal line, and as we can see here, most of this data is outside this line. It's not following perfectly this line. So we can state that our sample database is not normally distributed. So we can run an ordinary least square regression. We are creating here an OLS variable that's going to have all the information from this linear regression. Here we have a summary of our linear regression using the ordinary least squared method. We have the intercept, that is minus 64, and the distance is 1.8. So we can plot the cost per load against the distance, and we can add the OLS line together with the predicted values here in these red dots, and we can also add the confidence interval. So we see here the lower limit and the upper limits with a confidence of 95%. So now we can run the quantile regression. The first thing we have to do is to install and execute the package. The package is called QuantReg. So for me it's not necessary to install this package because I already have it on my computer, but I have to run this package using the library function here in R. We can draw again this cost per load against the distance, and we can add two interesting lines. The first one is the median regression line, that is in blue, and in red we can see the OLS line. So we're going to see in just a couple of seconds that this median regression line is a special case of the quantile regression when we use a tau of 0.5. So now we are going to define 4 different taus. These taus are 0.1, 0.25, 0.75 and 0.9, and we are going to run this quantile regression and plot the results. So what we get here is that we have 4 different quantile regression lines. Why? Because we define 4 different taus. So what we can state here is that in quantile regression we are going to have as many regression lines or quantile regression lines as taus we define. So here, for example, we have this quantile regression line for a tau of 0.10. The same happened here for a tau of 0.25. The same happened here for a tau of 0.75 and 0.9. And this one here in blue is the quantile regression line for a tau of 0.5. That is stated here. So now we can continue with another interesting plot. This plot is very common in publications about quantile regression. So what is this plot showing is that, for example, for the distance, that is our our explanatory variable, we have different values if we analyze different quantiles for a quantile regression method. So here in the x-axis we have the different quantiles, and here we have the different values for the distance beta coefficient. So if we remember just a couple of minutes ago, we ran the OLS and we got that the distance have a beta value of 1.8. So here we can see this 1.8 value. So this means that for the ordinary least squared method we are going to have always the same beta no matter which quantile we are analyzing. This is not the case for the quantile regression. In quantile regression we are going to have as many beta values as taus we define to analyze. So for example here, if we are working for example with the 25th quartile, we're going to see that the values for this quartile in the quantile regression is going to be completely different from this 1.8. In fact, these beta values are going to be lower than 1.8. We are going to check this in a couple of minutes. So now we are going to run this function we created. So this is the end of this, and we are going to clean all the data. So first, let's take a look on how the distance variable is distributed. So here we have that 396 miles is the cut for these 25% of the values. The same happened for 440 for the 50%, and 537 for 75%, and 1,673 is the 100% quantile. So we are going to create, just to check, ECDS function. For example, the distance, and we are going to calculate Q as the ECDF of a certain value. Let's say that we want to calculate which quantile corresponds for a distance of, for example, 405, I don't know, just a number. So here we see that this 405 miles corresponds to a quantile of 0.30. So what we are going to do here, we are going to run a cost per load forecasting function we created, saying that we want to know what is the predicted value for this 405 miles as a distance, using a tau of 0.5, because this 405 miles distance corresponds to a quantile of 0.3. So we run this, and we get that in this case the OLS states that the predicted value for the cost per load, given a distance of 405 and a tau of 0.5, is 666.99, and for the quantile regression we see that the predicted value is 617. So here we see that the beta for the OLS is still the same, but for the quantile regression we are using a beta of 2. So if we go to this graph, we are probably working on this area here, in this area for the quantiles, and in this area for the quantile regression. So here, for example, I split the values with different colors. Each color corresponds to a different quantile. So for example, we want to analyze the predicted value for a distance of 274. So we have here 274. I'm going to put some color on this data, and we see that the average for this is 355. Let's say 355. So this is the average. This is the average value for a distance of 274. So what happens when we run this in R. First, we can check, of course, the ECDF of let's say 274 is of course here, it's in the first quartile. So we are going to try to check what is the predicted value using OLS and the quantile regression method. So here we have 0.25. So the average value, we can say that this is the real value, for example, it's around 355, and we are getting for the OLS 430, and for the quantile regression we are getting 356. So it's the value we are obtaining using the quantile regression, it's almost perfect. We are very close, and we see here we are using a beta of 1.44, that is around here probably, and corresponds for a quantile of 0.07, so it should be around here probably. We can do the same for another values. Let's take one of the upper values, for example this one, 650. Let's put some paint. Let's try to calculate the average. It's around 1297. So we can come here again. We can calculate the ECDF of 650. It's 0.83. So we can do the forecasting for a distance of 650 using 1 as the tau, and as we see here, the OLS has a better estimation than the quantile regression. So what happens if now we go to 636? The average is around 951. So this value is 636. We are in the this quantile, so we can run this function. And again, we see that the OLS is estimating this value better than the quantile regression. So what we can see here is that we can continue with this analysis, but we need more information. Actually, we have only 409 lines of information. So we strongly believe that to continue with this analysis, we should get a bigger database in order to start analyzing different scenarios, as well to start including maybe in the analysis the different firms, or for example the different origins and the different destinations. So this was a brief summary of the different outcomes we are just analyzing, and our progress in our capstone project. We expect to continue our work in the following weeks, and we are also with a lot of enthusiasm in terms of seeing what is going to happen if we add more information to this CPL forecasting function we created. So thank you very much. Best regards here from Cordoba, Argentina, and from Mexico City. Thank you very much.